All right, everyone. Without further ado, since we're already past the 10:20 time mark, I'd like to welcome you to the Biochar and Commercialization session number 1D. All your phones are off, no photos, great. On that note, I'd like to introduce Matthew Kieffer from RT. Take it away.
Good morning, everyone. Can you hear me in the back okay? Yeah? Okay.
Can you get a little closer to the microphone?
Yeah, let me see if I can switch this a little bit. Is that better?
Yes.
Great, okay. First of all, thanks everyone for coming. It's been a great conference so far. Have a couple of great sessions left today. Today, we're going to talk a little bit about ARTI and optimizing biochar production machines to maximize your revenues as well as your carbon credits associated with it. So my name is Matt Kieffer. I'm with ARTI. We'll go into a little bit about ARTI, so you have a background understanding of what we do, the equipment we produce, and then we'll jump into the scenario analysis following that. So ARTI is based out of Iowa. We are a 10-year-old company, and we focus on a lot of different things surrounding biochar. You can see the points up here. We focus on manufacturing reactors, producing biochar, sequestering CO2 and consulting around biochar. We do techno-economic analyses and life cycle analyses. And then we also do research and development. And this is honestly one of our favorites. We love working in biochar projects, whether that's producing biochar itself, evaluating feedstock and biochar, evaluating applications for biochar, whether that's running solar pumps to filter water through a biochar filter, or if we're filling filter stocks with biochar. We love evaluating different projects. We love talking to customers that have different applications for their products. So those are a couple of things that we focus on, mainly focus on manufacturing the reactors and then also the research and development piece as well. So this is what we're going to be talking about today. We're going to give you an introduction about the equipment that we use to produce our biochar, so you have an understanding of how that flows throughout the scenarios that we're going to analyze. We're going to give you an overview of a couple of different scenarios. We're going to look at different co-products associated with different production scenarios, and then we're going to jump into some of the numbers. I know it might be a little bit hard on the screen to see some of the numbers that we put up there unless you have a pair of binoculars in the back, but bear with me. I'm going to try to walk through some of that and highlight some of the main points associated with that. So first of all, our biochar production units. This is our base single train unit. It is housed in a 40-foot shipping container. You can see in the top right. It's a fully automated semi-mobile unit. So you can pack it up, you can move it to the site that you want if there is the infrastructure available on site to process the equipment. This machine you can modify. You can increase the capacity of it. We'll dig into some of those details later. Excuse me. But we have a single train, a 3-train unit that we run in parallel. All trains run parallel. And then we have a 5-train unit. And obviously there are benefits with scaling up inside of a single container, increasing the capacity, reducing that CapEx cost per ton of biochar produced, and maximizing the revenue associated with it. We'll jump into that a little bit later. That's an overview of our system. Just to give you an idea of the scale and the processing of the system, this is one of our single train units. On the left-hand side, that's out of the picture, you'll have a walking floor trailer that'll carry the biomass up to a biomass bin. Enters the container. We have a drying unit that utilizes recycled heat from the system. It dries it. It goes from the left side of the reactor to the right, all the way down drying. Drops down into the pyrolysis unit, and then pyrolyzes from the right side of the reactor, excuse me, all the way to the left. When it gets to the left-hand side, you can see it enters the biochar removal chamber or cooling chamber, where it extracts it, drops it into our biochar handling, and it distributes the biochar amongst the super sacks. So these are scenarios we're going to analyze today. On the left-hand side, you see 3 scenarios: the single train, 3 train, and 5 train. We'll look at those to start, and then we'll jump into a couple of add-on technologies as well, including solar panels, bio-oil production, waste heat production, and implementation of an afterburner and the benefits associated with each. Now keep in mind, these are a lot of scenarios, and I'm talking for about 15 minutes. There's only so much detail that we can cover here, and there's a lot of information that goes into this. Typically, we like to use Monte Carlo simulations to look at the probability of the outcomes associated with the different scenarios. You have varying parameters, you have varying prices of products. So the scope of these analyses can span a very wide range, as you might know if you're in the biochar industry. So keep in mind, this is a static analysis. There's a lot of assumptions that go into this that can change. So sometimes be wary of the numbers. Don't focus necessarily on all the details, but think about the bigger picture, ask those questions. We want to look at how we can maximize the revenues and the corks, the CO2 removal credits associated with these. So what we're going to do is we're going to take a base scenario. We're going to have our single train. We're going to look at that, and then we're going to compare that to every other scenario as well to see how they stack up against each other. I'm going to read through the assumptions on the left-hand side, and those are going to stay pretty consistent throughout the rest of the scenarios. I'll highlight what components we're going to change. But for the base case scenario and all of our other scenarios, we are using a soft wood chip. This is based off of a trial run that we did, operating at 700 degrees C. We take all that information, our processing parameters, the throughput, the biochar output. We look at the emissions profiles. We've done the analysis on the emissions, and we take that all into account. And we have built out our LCA and our TEAs associated with it. So we use all that information from our trials that we've done, and we feed it into our models, and that's what these scenarios are based off of. So with this, like I mentioned, 281 days per year that we're going to be running in this model. Biomass throughput of up to 8 tons of biomass on a wet basis per day. That can fluctuate, keep in mind. We have a moisture content of 18%. Biochar hydrogen to carbon ratio of 0.34, biochar yield of 29%, carbon 90%, revenue streams of biochar and our carbon credits for this base scenario. We have our biochar produced annually, our selling price for our biochar at $540 a ton. We have a cork selling price at $100 per credit. So those are going to carry out through a lot of these scenarios. You're going to look at the top right-hand side, you're going to look at a little bit of the carbon balance for our corks that we're generating. And that's going to look at the same for each analysis. Here we're sequestering in the biochar about 2.66 tons of CO2 equivalent per ton of biochar. We are emitting about 0.29 tons of CO2 equivalent per ton of biochar. And you take the net balance and you arrive at 2.37. Right, so this is the base number we're going to be comparing against. We're going to increase or decrease and look at the results associated with it. So from the bottom right-hand side, you got your single train. You have 1.9 tons of biochar being produced. You have an investment cost of $620K, and then you have a net present value of $443K. We also are going to include a couple of other numbers. You have your annual corks revenue, and then we have our other revenue streams in the slides as well. So this is our base scenario. We're going to look at this and we're going to compare. One thing to keep in mind as we go through this is for a wood chip, a homogeneous wood chip scenario that has relatively low moisture, and there are not many contaminants, no rocks, no other big things that are causing disruptions in the system. So we're going to have a continuous system here, but keep in mind, in reality, there's a lot more challenges associated with it. First of all, we're going to look at capacity, increasing capacity. So looking up to 3 and 5 trains, you have a pretty big increase in your capital costs up front. But everything else generally remains pretty similar. So we look at the top right, you look at your corks. So instead you're reducing the total CO2 equivalent produced per ton of biochar in the 3 train and the 5 train compared to the single train reactor. So you have, instead of 2.37, you go to 2.46 and 2.48. And that shows up in the revenue streams, both from the biochar and from the corks that are being sold. If you look at the summary table on the bottom right, you can see the 3 train and the 5 train. The biochar produced goes up to 5.7 and 9.5 tons per day. The investment jumps up quite a bit. If you remember back in the single train scenario, it was about just above 440 or 620K. Now we move up to 1.19 million and 1.36 million. So the capital cost, it does go up, but it doesn't go up linearly with the amount of biochar that you're producing. You take a look at the last row there, the net present value. You have 1.74 million for the 3 train and 3.6 million for the 5 train. With those assumptions, clearly the 5 train, as you increase capacity, you're going to increase that potential for net present value with the additional capacity for production, and then the reduction in the capital cost per ton of biochar produced, and the corks per ton for your capex per cork produced as well. So initially, the capacity is a pretty promising technology, I guess, to consider, or approach to consider. So this is a picture of our 3 train unit. It's being commissioned. As you can see, similar structure to our previous single train, with a little bit more equipment on the outside to handle some of the larger volumes of the heat flow throughout the system. So now we're going to look at a couple of add-on scenarios. So instead of increasing the capacity, we're going to stick with a single train scenario. And why are we going to look at this? We're going to look at this, one, to reduce costs associated with the electricity that you're going to be using in your system. 2, you're going to reduce your dependence on potentially higher carbon producing electricity sources, right? So you're kind of hitting it from 2 angles. So you're going to have a little bit of a capital cost increase associated with the panels. They're 8 kilowatt panels. You're assuming 100% coverage of the electricity usage in the system with net metering. Your revenue stream, instead of just biochar and corks, now is biochar, corks, and electricity savings. Assuming electricity price, 15 cents per kilowatt hour, and a biochar price and cork selling price similar to what we had before. We look to the right and we see, we look at our cork values. Now, instead of 2.37, we bump it up a little bit to a 2.41, simply with reducing or changing that source of electricity. Looking down in the right-hand corner, you have on the left-hand side your solar inclusion, on the right-hand side your base case and the single train. Your investment goes up 35K, your net present value goes up about 50K. Down in the bottom, the orange, you can see the cork revenues. Just for going up from 2.37 to 2.41, you see a jump from annual cork revenues of 126,000 per year up to 141,000 per year. And this is something that can swing pretty wildly, depending on your system, depending on the characteristics of the system. That cork value can slightly change, but this is over a 5-year period. My apologies for not mentioning that, but over a 5-year period, that can have a pretty big impact. 5 years pretty short. We've heard people talk about 30-year periods, right? That amount of change in a 30-year period can have a very large impact on that revenue stream. So something to keep in mind. Small changes can lead to big results. The next scenario we're going to look at is bio-oil generation. This is looking at a system, instead of using all the syngas to go into a dryer, to go into the pyrolysis unit, and then flaring the excess heat, you're assuming that you can capture some of that, condense it into a bio-oil. With bio-oil systems, you have a little bit higher capital cost. We're assuming here about $150,000 of capital cost with this single train system. With higher capacities, you're going to have different needs for volume. But you have a bio-oil price, so you're selling the bio-oil. You have bio-oil collected of 1 ton per day. And you move up to the corks. You can see you're reducing your CO2 equivalent produced per ton of biochar from 0.29 down to 0.11. So you're jumping from 2.37 to 2.55, right? And there's some tricky things here with the carbon accounting or the carbon allocation for your co-products and the CO2, but that's a pretty big jump, right? However, you also have the higher capital costs associated with the equipment you're using to pull that out. So if you look down in the right in the comparison between the bio and the single train, you have a jump of 150K. In the capital cost, you have net present value also jumping about 50K. So higher capital cost, higher corks, but they balance out a little bit, and you have a similar situation as the solar panel inclusion. Before I jump into waste heat, I'm going to have a summary table at the end that's going to look at each scenario next to each other. It might be hard to track these, but there will be a summary table that hopefully will be helpful at the end as well. So now we're looking at waste heat. Waste heat, there's a lot of opportunity. This is there's a lot of potential with the waste heat here. We're looking at one scenario of utilization of the waste heat, but in theory, you can utilize waste heat in a lot of different scenarios depending the market that you're in. So for us, we're looking at potentially drying additional biomass. You can look at heating, right? You can look at electricity generation. Depending on the market you're in, you're gonna have different advantages on what approach you're gonna take. You're gonna have higher capital costs associated with electricity generation. You're gonna have lower capital costs with propane displacement if you're just doing heating of a building. So there are pros and cons with different scenarios. So keep in mind, think big picture when thinking about waste heat utilization and the inclusion of that, the equipment that needs to be included in your system. So with this, we look at the cork values. So you have a increase from 0.29 up to 0.31. Looking back to the total CO2 sequestered, you have looking at displacing propane associated with systems. So you have a bump there as well. So when you look at the net CO2 sequestered in biochar per ton of biochar, you arrive at 2.37 for the base scenario, but then you're looking at 2.75 total, looking at the biochar and displacing by the propane. Looking down on the right-hand side, you see a little bit higher capital cost investment, but you also see higher net present value, and that's with the value streams associated with the drying that we assumed in the assumptions. Your cork revenues go up from 126K per year up to 160K per year. So over the lifetime of the project, that has a big impact on the net present value. I'm going to move on to the last scenario. I know we're moving pretty quick, but we'll leave time for some questions. This is the Afterburner implementation. So when people think co-products of the system, the profitability of the system, we're surprised. Not often do people think about how do you reduce the CO2 impact of your equipment. And you think about the waste streams that are coming off your system. So instead of producing something else, now you're reducing something else. So you're looking at how can you change the flue gas stream to reduce your carbon footprint. And what we do is we focus on the particulates that we were seeing in our trial. There's a lot of particulate matter, there's methane, there's carbon dioxide or carbon monoxide. These all have varying levels of impact, and we saw that particulate matter, particularly, no pun intended, had the highest impact on that value. So by including an afterburner, low capital cost, pretty simple implementation, you can have a large impact on your cork value. So by doing that, we increase from 2.37 up to 2.4 in our cork value. We have relatively low investment costs, change in investment costs from 620K up to 680K, and then your net present value jumps from 443 up to 465. So you see an incremental cost with very little change in upfront on the biochar system. So this is keep in mind that there's not always, you don't have to implement a really extreme solution in order to increase the value of your equipment. There are creative ways to knock up this value of the cork credit to highly increase the value of your system. This is a picture of one of our units in Iowa. I'm doing an emissions test so that we can analyze those flue gases, those those off gases, so we can look at what including an afterburner does to those emissions, how we can change our cork value so that when building out our TEA models, our LCA models, and working with clients, we can figure out how to best implement a solution to improve the revenue streams. Lastly, we have a summary table here. There's a lot of information on this slide, a lot of numbers, but on the top chart, what that is the total corks produced over a 5-year period for a project. So you have all the scenarios we looked at, a single train, 3 train, 5 train, then we have solar inclusion, bio-oil production, waste heat, utilization, and then implementation of the afterburner. Clearly, the increase in capacity drastically increases the number of corks you're going to generate, but then you have the capital costs associated with it. Looking at the add-ons, in this chart, the axes, they look like marginal changes, but depending on your project scale, those can have significant impact in the revenue streams. The bottom table, it shows the net present value, your total investment costs, annual corks, annual biochar revenues, your cork ratios, and your total corks produced over 5 years. I'm not going to put you to sleep and read through all those, but feel free to take a picture. Feel free to have this conversation with us, because at the end of the day, our goal and your goal is to maximize the revenues of your biochar production units. Whether it's an RD unit, whether that's another unit, you need to think about the big picture. Think about those different systems that you can include to take advantage of different portions of the system. I'll wait till a couple of phones drop. Please feel free to come talk to us after as well. And this is my last slide. This is just a footprint of Artie. Our consultancy services, a lot of projects we're working on in blue, so we're all over the place. We have reactors and equipment in the orange dots, so we have those operating in a lot of different locations. We have our offices in Iowa, as I mentioned, but we also have an office in Quito, Ecuador. So we operate in North and South America, and we're always looking for new projects. Excited to hear what you're working on, so please don't hesitate to come and talk with us and explore some of your projects with us. And that's it for me. I'll open it up for questions.
And I think at this point I say, yes, the gentleman on that side of the room.
Yeah, I'm just curious what the feeds, like the assumed feedstock price is in that model, in your model.
Oh, that's a good question. I think we use $30 per ton of feedstock on that. We did not include that in the slide, but I believe it's $30 a ton for that softwoody
So
biomass.
it's included in those
Correct, in the assumptions. Yep,
Okay,
yep.
thank you.
Which is for us a little bit high on the price side. We like to utilize feedstocks that are readily available. Oftentimes you're not going to have as pure, but when you're talking softwoody biomass that's high quality, you're going to pay a little bit for it, but you're also going to reap the benefits in the processing of those wood chips as well. You're going to reduce a lot of headaches in the operation of the system. Your automation system is going to operate a lot better. But yeah. Any other questions?
I noticed your calculations were for 24/7 operation. I was curious about the other 84 days and what those were taking up.
So those days, so we operate 280 days a year, is the assumption in this model, right? Obviously that can change. It can go better, it can go worse, and it just depends on the system and the feedstock. Those days are often included in takedown and maintenance. You might be replacing parts, you might be changing out equipment that's exposed to high temps and oxygen, but usually it's adjustments of the automation model, replacing of components, and any cleaning that needs to be done.
Excellent.
And I need to cut you off.
Ah.
Sorry to say.
No, sounds good. Thank you. Thank you.
Very good, thanks, man.
I'll grab that after.